So far, we calculated the periods of lots of oscillators, pendulums, springs, rulers, hula hoops. We gave them a kick, moved them off equilibrium, and then they were oscillating at their own preferred frequency. Today, I want to discuss with you what happens if I force upon a system a frequency of my own. So we call that forced oscillations. I can take a spring system, as we had before. This is x equals 0. This is x. And we have the spring force, very familiar, minus kx. But now, this object here, which is mass m, I'm going to add a force to it, F0, which is the amplitude of the force, times the cosine of omega t. So I'm going to force it in a sinusoidal fashion with a frequency that I choose. This frequency is not the frequency with which the system wants to oscillate. It is the one that I choose. And I can vary that. And the question now is, what will the object do? Well, we have Newton's second law, ma equals minus kx plus that force, F0 cosine omega t. A is x double dot. So I get x double dot plus, I bring this in, k over m times x equals F0 divided by m times the cosine omega t. Now the question is, what is the solution to this differential equation? It's very different from what we saw before, because before we had a 0 here. Now we have here a driving force. It's clear that if you wait long enough, that sooner or later that system will have to start oscillating at that frequency. In the beginning, it may be a little different. In the beginning, it may want to do its own thing, but ultimately, if I take you by your arms and I shake you back and forth, in the beginning you may object, but sooner or later you will have to go with the frequency that I force myself upon you. And when we reach that stage, we call that the steady state, as opposed to the beginning, when things are a little bit confused, which we call the transient phase. So in the steady state, the object somehow must have a frequency which is the same as the driver, and it has some amplitude a. And I want to evaluate with you that amplitude a. So this is my trial function that I'm going to put into this differential equation. X dot equals minus a omega sine omega t. X double dot equals minus a omega squared cosine omega t. And so now I'm going to substitute that in here. So I'm going to get minus a omega squared cosine omega t plus k over m times a cosine omega t, and that equals F0 divided by m times the cosine of omega t. And that must always hold. So therefore, I can divide out my cosine omega t. I can bring the a's together. So I get a times k over m minus omega squared equals F0 divided by m. Now this k over m is something that we are familiar with. If we let this system do its own thing, we bring it away from equilibrium and we don't drive it, then we know that omega squared, which I will give a 0, equals k over m. This is the frequency that we have dealt with before. This is the driving frequency. It's very different. And so I'm going to substitute in here for k over m omega 0 squared. And so I find then that the amplitude of this object here at the end of the spring will be F0 divided by m divided by omega 0 squared minus omega squared. And this amplitude has very remarkable characteristics. First of all, if I drive the system at a very low frequency, so that omega is much, much smaller than omega 0, We call omega 0 often the natural frequency. It is the one that it likes. If you have omega much, much less than omega 0, this goes. Omega 0 squared is k over m. So you get an amplitude A, which is f0 divided by k. If you go omega way above the natural frequency, or let's say omega goes to infinity, becomes very, very large, then downstairs becomes very, very large, so A goes to 0. But now what happens when omega is exactly omega 0? Then the system goes wacky. Look what happens. The downstairs becomes 0, and the amplitude goes to infinity. And that's what we call resonance. So if we drive it at that frequency, the system goes completely berserk. I can make a plot of A as a function of frequency. When I say omega, you can obviously always change to hertz if you prefer that, because omega is 2 pi times f. So you can do it either in hertz or you can do it in radians per second, of course. So if I make a plot of the amplitude versus frequency omega, then at low values, I have here f0 divided by k is the amplitude. When I hit the resonance frequency, the natural frequency of the system, it goes out of hand, goes to infinity. The moment that omega is larger than omega 0, notice that the amplitude becomes negative. A negative amplitude simply means that you get all of a sudden a phase change of 180 degrees. So the object is 180 degrees out of phase with the driver. I will not expand on that too much today, but it is negative, and so it comes up here, and then it goes here to 0 for very high frequencies of omega. So something very spectacular is going to happen at the resonance frequency of the system. In practice, of course, the amplitude will not go to infinity. And the reason for that is that there is always friction of some kind, there is always damping, but you get a very high amplitude, but not infinitely high. So if I make you a more realistic plot of the amplitude, and I will take now the absolute value, the magnitude, so we don't have to worry about it getting negative, we don't have to worry about the 180-degree phase shift, then you would get a curve that looks like this. And here then, if this is frequency f, then here you would get the natural frequency when things go out of hand. And depending upon how much damping there is, this curve would look either very narrow and very spiky, goes very, very high, then there is very little damping, or if there is a lot of damping in the system, it's more like this. So the narrower this, we call this the resonance curve, the narrower that is, the less damping there is. I have here a system on the air track, which is an object that I can drive with a frequency that I can choose. Here is a spring, object, mass m, and here's another spring. It's fixed on this side, right there, and here I'm going to drive it. So I have here this variable force that you see there. And what I want to show you now is that first I will drive it at a frequency which is way below the resonance frequency. Then you will see an amplitude, not very large. I will then drive it way above the resonance frequency. Again, you will see an amplitude which is very low. If I can go very high frequency, you will see that it almost stands still. And then I will try to hit the resonance frequency, and that will be, it's about 1 hertz, the resonance frequency. If I just let this object do its own thing, just this, now you see the natural frequency. It's about 1 hertz. But now I'm going to drive it here with a system, and we're going to pull on this spring with a frequency that we control. So let me start. You see here the frequency, you see an indicator, very low, way lower than 1 hertz. And when you look at the way that the system responds, if you wait long enough, when the transients are died out, you will see that they go hand in hand, that the amplitude is in phase with the driver. That's why we have plus amplitude here. But the phase is not so important today. But see, they go hand in hand. Very small amplitude, roughly F0 divided by K, which is the spring constant of the spring. Now I'll go way above resonance, and this system will slip here. So don't pay attention to the arrow anymore. Way above resonance. You see it starts to slip. And look at the amplitude, very modest, very small. But we went over this curve. So first we probed it here, and now we're probing it here. Look, it's almost not moving at all. Almost standing still, and I'm driving it with high frequency now. And now I'm going to find you this resonance, which is near 1 Hertz. Which is somewhere here. And look. Very high amplitude. If we're not careful, then we can actually break the system. Very high amplitude. I'm trying to scan over it now. Go a little bit off resonance. Now I'm back on resonance. See, with a huge amplitude. Better turn it off. So you see here the response when I drive a system. When my system is a little bit more complicated, for instance, if I had 2 masses here, so I would add one here, spring constant K, spring constant K, I could repeat this experiment. And if I did that, I would find 2 resonance frequencies. And if I do it with 3 objects, I would find 3 resonance frequencies. If I did it with 5, I would find 5 resonance frequencies. And when I make then this curve of A amplitude as a function of frequency, either hertz or in radians per second, whichever you prefer, then if I had 3 objects there in a row, you would see something like this. And depending upon how many of these objects you have, you get more and more resonances. And these resonances can all be found by driving the system and searching for them. If I go to a system whereby I have an infinite number of these masses, we call them coupled oscillators. These oscillators are coupled through the springs. An infinite number of coupled oscillators would be a violin string. Here's a violin string. And the reason why I call it infinitely number of oscillators is that I can think of each atom or each molecule as being driven, as being connected by springs to the neighbor, and so it's an infinite number of coupled oscillators. And so when I start to shake this system, I would expect a lot of resonances, and that's what I want to explore with you now. In the case here that the objects move in the same direction of the spring, I call this the y direction, and I call this the x direction. So the spring is in the x direction, the objects, the beats are in the x direction, and the oscillations are in the x direction. We call those longitudinal oscillations. There is also a way that you can have transverse oscillations, transverse, whereby the motion is in the y direction, whereas the beats are in the x direction. I could even do that with this system. I could make them oscillate like this, because the springs will obviously also work if I do this with the system. And that's the way I want this violin string or piano string to oscillate now, because that's the only meaningful way that I can make it oscillate. And so I wonder if I'm going to drive it here by shaking it up and down, searching for the resonance frequencies, what I will be seeing. If I go with very low frequencies, the string laughs at me. The string does nothing. It's just bored. It doesn't respond to me. I am somewhere here in the resonance curve. But then when I increase the frequency, slowly I hit the very first frequency at which it likes to oscillate. I call that F1. And when I look at the spring, and you will see that shortly, the string will oscillate like so. It will go up here, and it will go down here. And all it will do is this. That's his first resonance, and I call this n equals 1, often called the first harmonic. And then I go to higher frequencies, and it will not do very much. It's very unhappy. And then all of a sudden, I hit a second resonance. I call that F2. And the second resonance will show up like this. This point of the string will not move at all. When this part is up, this part will be down. I call that n equals 2. And it oscillates like so. And this point, which is not moving at all, we call that a node. I go a little bit beyond that second resonance, and nothing happens. The string will be quite unhappy, sort of flutters a little bit, until I hit another resonance, F3. And then, with the next resonance, I will see two nodes appear, one here and one here. And the string will oscillate like so. This goes up and down, 180 degrees out of phase, and these two ends are in phase. This is n equals 3. And I can go on like that and add nodes, and I will show you some of that very shortly. The frequency that I generate, I call that f of n is an integer, it could be 1, 2, 3, or 4, is linear in f1. In other words, if f1 were 100 hertz, then f2 would be 200 hertz, and f3 would be 300 hertz. We call n equals 1, we call that the first harmonic. Some books also call it the fundamental. I will call it the first harmonic. And we call n equals 2 the second harmonic. And so on. N equals 3 is the third harmonic. So we're going to get a series of discrete frequencies which are equally spaced. F1 depends on the length of the string, on the tension. I will write tension, don't confuse this with period, and it depends on the mass of the string. Without going into the detail how the dependence is, these are the parameters that determine the first harmonic. I have here a very special violin string, or piano string, whatever you want to call this, and we can generate these resonance frequencies by searching for them. And I would need assistance from a student. Would you be willing to help me? So you hold one end of the piano string in your hand. Don't let it go, please, don't let it go. I promise you I won't let it go either. Okay, so I put a certain tension on it, and I start to shake at a very low frequency. Look how low. And look how happy this string is. Nothing. It just laughs at me, it ignores me, it doesn't like me. Now I'm going to increase the frequency. And now I'm hitting the first resonance. It's coming up. There it is. And that's exactly the shape that you see on the blackboard. Very clear. I shake it here. I have exactly the resonance F1. Let me now try to hit the second harmonic. If I go up a little over the F1, then nothing much happens. It's hard for me to see. Is this the second harmonic, or is this already the third? It's already the third. Let me see whether I can get the second. I think I got it now. Do I? Okay, so here you see the second harmonic. You see indeed that note, that point standing still. And the amplitude is enormous. That's a characteristic for a resonance frequency. We call it also a normal mode frequency, or a natural frequency. It's all the same thing. Let me now try to generate one that is very high as I possibly can. and you tell me which harmonic it is. All you have to do is count how many notes there are, not counting my hand and his hand, and you add 1, and that is the harmonic that I generate. The system is not too happy. You see, you feel it sort of when it comes, yeah. No. I see now I'm off resonance. It's very hard for me to hit resonance, but I will get it. There it comes. There's no question now. I got it, I'm on resonance now. Look at it. Clearly I'm on resonance. So how many did you count? 6 harmonic? Look, 12 to me, but okay, you count better than I can. Okay, thank you very much. So you see here how a system responds to a driver, and a complicated system like a string has many of these resonance frequencies, which we call the normal modes. Now when you have a violin, you have 4 strings. They all have the same length. There are musical instruments like a piano, whereby the length is different. Violin, 4 strings, all the same length. You can set the tension. Tension is changed normally when you tune the instrument before you start playing, but these 4 strings all have a different mass, and that gives them a very different frequency. Now, if you play the violin, you cannot change the tension, of course, during the playing. That would be a little difficult, although there are instruments that exist where actually the playing depends on the tension of a string. With a violin, that's not the case. So with a violin, the only option you have while you're playing it is to make the string length shorter. And you do that by moving your finger along the string. By making it shorter, the frequency goes up, and by making it longer, the frequency goes down. Now, how do you excite a musical instrument like a piano string or a violin string? There is nothing that is driving it exactly at that resonance frequency. So if you want to get a 440 hertz out of a violin string, then you're not driving it exactly at the 440 hertz like we are doing. Well, that's true. But if you take a bow and you rub the string with a bow, then in a way what you're doing is you are exposing that string to a lot of possible frequencies, not just one, but it is a rubbing action. I could also rub it with my finger, or I could pluck it, or I could kick it. And what it does, it ignores all the frequencies which are not at resonance, but it picks out the ones which are at resonance. So striking it with a bow is effectively exposing it to a whole large spectrum of frequencies, and it picks out the ones that it likes. In fact, if you strike a violin string with a bow, you may excite it simultaneously in the first harmonic and in the second and even in the third harmonic, or even higher harmonics, and that makes the difference between the various instruments. That gives it a special tone quality. Depends upon the cocktail, the combination of the various harmonics that you excite. Now, if you go to woodwind instruments, then the situation is quite different. I have here a sound cavity. It's a box which has length L, and there is air inside here. And I want to see whether this system has resonance frequencies. So I put in here a little loudspeaker, generate sound with different frequencies, and search for resonances. And there are. The resonances of this system, however, are different from the string in that sense. It's not the box that will resonate here, but it is the air itself that starts to resonate. Air acts like a spring. In fact, in that sense, it is very parallel to our spring system. It is also a longitudinal oscillation, whereas that is a transverse oscillation. So you make pressure waves inside, and if you do that at the right frequency, the air acts like a spring, and then you get strong reactions, which are the resonances. In this case, the nth mode, the nth harmonic, is given by n times the velocity of sound divided by 2L. And V is about 340 meters per second at room temperature, so it is the sound speed. Notice it's again linear in n. In other words, if an instrument produces a certain frequency, let us say that L equals 25 centimeters, Then you can calculate the frequency f1. You know what the speed of sound is, 340. So we take n equals 1. So the frequency that we would get equals 340 divided by 2L, which is 0.5 in meters. And so that gives me 680 hertz. So that would be this big, would give you 680 hertz. But the second harmonic, F2, will be double that. So it will be 1360 hertz, and so on. Now this system, which is closed on both sides, wouldn't be a very good musical instrument because your sound would not come out. So what people do, they make them open. A sound cavity, which is just open on both sides. Like this, for instance. This is open on both sides. And even though it may surprise you, if we put a little loudspeaker here, we can excite the air column even in this open system in a complete similar way than we do it here in this closed system, and we get exactly the same series of frequencies that I put here on the blackboard. There are also musical instruments which are open on one side and closed on the other. So this is called an open-open system, and this would be called a closed-open. Clarinet is closed-open. Here I can also get a series of resonance frequencies, even though here the series wouldn't be exactly like this. It's a little different. It doesn't matter now how different, but it is a little different. But you get, again, the whole series of resonance frequencies. So again, you see that if I make the system longer, then I get lower frequencies. So if I make the length 1 meter, yay big, then I would get a frequency F1, which is about 4 times lower than the one that I have there, which is 170 hertz. And the second harmonic would then 340 hertz, and so on. So when you see an organ in a church, you see all these organ pipes, different lengths. The long ones have the very low tones, and the short ones have the very high tones. And that is the way that these instruments work. I have here a wind organ, which I have demonstrated to you before. It is open on both sides. And because it is corrugated in a very special way, when I blow wind past it, it will go into resonance. That's to say, wind here is like a spectrum of all possible frequencies. It's like the bow on the violin, and then it picks out the frequencies that it likes. However, if I increase the speed of the wind, I can try to force it into higher frequencies. So at low wind speed, I'm more likely to hit the lower harmonics. At high wind speeds, I'm more likely to hit the higher harmonics. This one is 71 centimeters long. It's open. And if I were able to hit the first harmonic, that would be a frequency of about 240 hertz. I may not be able to excite the lowest harmonic, the first harmonic, but I'll try. But certainly the higher harmonics are very easy to excite, and I can make you even listen simultaneously to more than one frequency. Just like the violin string, when you strike it, can simultaneously oscillate in a combination of these modes. So let me swirl this around. I'll first start low. This may be the second harmonic, 480 hertz. This is definitely way higher. This is again the second harmonic, 480 hertz. Were there times that you heard two simultaneously? I hear two. If you play a flute, then you do the following. You make holes in here. And when you take your fingers of both holes, then the effective length of the flute is this long. You get a high tone. If you put your finger on this one, then the effective length of the flute is this long. You get a lower tone. If you put your finger on both, the effective length of the flute is this long, and you get an even lower tone. I have here a very special flute, open on both sides, and here you see the two holes. So we'll first close the two. That gives us the lowest frequency. That you play the flute. So it's simply a matter of making the instrument longer or shorter. I have another example here of an instrument which is open here, and here it is closed. This is my version of a trombone. There's a piston here. So this is a system that is like this, but I can move this in and out. And so when I have it far in, the frequency would be high. And when I have it here, so you see it's directly related to the length of this trombone. And if you learn how to play, you can try to play a tune. I'll try. Thank you. Resonances are all around us. When you drive your car, you may have noticed that all of a sudden you hear some crazy rattle somewhere. It could be your mirror, it could be something else, it could be an ashtray. Because you're driving it and you're exciting it with the frequency with which the wheels go around, and you may hit a resonance frequency. You go a little slower and the rattle stops, but something else may start to rattle. The reason why the first rattle stopped, because you go off resonance. But you may go on resonance of another object. All objects that you have in your room have preferred resonance frequencies. Whether it are the pots or the pans or whether it is your refrigerator or anything you can think of. Everything has resonance frequencies. Your body has resonance frequencies. If I took you in my hands and I would start to shake you, then if I do it at low frequency, not much would happen. But there would be one frequency that your arms begin to move like this, like they're physical pendulums, right? And if I hit that frequency, then indeed there would be a strong response. And so your body has many resonance frequencies. Your arms, your legs, your head, everything. We also experience, all of us, emotional resonances. A small input, a huge output. Falling in love is an emotional resonance. If someone touches a sensitive nerve, that is a resonance. Someone could say something to you. And it could be a very sensitive issue for you. And you go non-linear. Your response is unbelievably strong. That, in my view, is also a form of an emotional resonance. I have here two tuning forks. And these tuning forks are designed in such a way that all I would have to do is just bang them. And they will pick out their own resonance frequencies. The tuning fork is very simple, like this. I give it a kick, and the kick is like dumping a whole spectrum of frequencies on it, and it picks out the ones that it likes, which is this one. And that's the one in which it will resonate. It's possible that I can excite it at higher frequencies, at higher harmonics, but that's a little hard even with a tuning fork. So this one is 256 hertz. So the prongs move 256 times per second, and this one is 440 hertz. And you hear no overtones. You don't hear higher harmonics. If I take something as simple as a wine glass like this, it has many, many normal mode frequencies, many resonance frequencies. The lowest one is very easy to excite, and I will do that. I will rub it with my finger. Rubbing is like striking a string with a bow. It's all the same. I expose it to lots of frequencies, it ignores them all, it picks out the one that it likes, the resonance frequency, the normal mode, the natural frequency. And what the glass will do in its lowest harmonic, in its first harmonic, it will sort of oscillate like this. And I will show that to you later in this lecture in slow motion. But let me first make you listen to the frequency. It's around 470 hertz. I have to wash my hands because I have chalk on my fingers. And because of the chalk, I will not be able to excite it. I have to really rub it with some liquid. And therefore, my hands have to be chalk-free. Chalk is just too greasy. Let me try. Very clear. I remember when I was a student, we had after-dinner speakers. If we got bored, we would all do this. Let me tell you, that makes a lot of noise. So again, I'm not exciting it with the 470 hertz. I'm dumping a whole frequency, a whole spectrum of frequencies on it, and it picks out the one that it likes, which in this case is the 470 hertz. Resonances can be destructive, and rumor has it that there are singers, women who take a wine glass, and they do exactly what I did. They do this. They listen carefully. They generate that frequency with their voice. They increase the volume of the voice, and then the rumor has it that, bang, the glass goes. In other words, the amplitude of the glass becomes so large that you get so high, so close to resonance, and so much power goes into it because of the volume of the voice that the glass breaks. I'm going to try to break a glass with you, and you'll see that it is not easy. I have here a wine glass. It's almost the same as the one I have here, there. And we can illuminate that glass with a strobe light, which you see here, and I'm going to show you there the display of that strobe light. And the reason why we strobe it is that we want you to see, as we excite the exact frequency of the glass, we want you to see the motion of the glass. And the way we can make you see the motion is by strobing it not exactly at the frequency of the sound, but a little bit different frequency. So you will see the stroboscopic motion then of the glass. So I will make it darker shortly, but I want you to see at least most of this. I can generate then the 470 hertz, which is very close to the resonance frequency. This is the tone that we will use. We will increase the volume, and then we will try to hit that resonance just right. We may be off by a few hertz. We have to be right on within a hertz, and then we'll see where we can make the glass break. Now, I want to warn you, the sound is going to be very strong. So you may, as the time goes on, as we go to higher volume, you may want to close your ears. In fact, I will use this to protect my ears, and I will even use this to protect my eyes, in case the glass might break, which I doubt whether it will, but who knows. All right, so let's make it very dark. So you see here the glass. It's not doing very much. And I'm now going to increase the volume of the sound. I'm going to cover my ears now. You already begin to see some motion. I'm not sure that I am on resonance. Increase the volume. I'm now changing the frequency. Getting very close. Getting very close. There it goes. I mentioned that resonances can be very destructive, and there are some striking examples in history. In fact, you may have, when there's a storm, you may have seen the traffic signs, which just a sign on a pole, that the traffic sign starts doing this. Which is strange, because there's a wind. A wind is like a spectrum of all kinds of frequencies. It's like blowing air into a musical instrument. And then this traffic sign just picks out the frequency that it likes. And then, if the wind is strong enough, it could be very destructive. And the most striking example of destruction is that of a bridge which was built, and that is the Tacoma Bridge, the West Coast, which is very dramatic. And of course, I will have to show you that movie. You will see what the wind can do to a bridge. So we'll start this movie, and then we'll make it dark. Amazing. Amazing what resonance can do. With musical instruments, we're stuck to the speed of sound in air, which is 340 meters per second. And when I speak to you, I have here a sound cavity, which has a certain size, a certain shape, and while I speak, the size and the shape changes all the time. And that gives my voice a very characteristic sound that makes it possible for me to make a low sound, makes it possible for me to make a high sound. And no matter how I speak, you will say, yeah, that's no question, that's Walter Lewin, that's clear. It's very recognizable. Each one of you and I have a very well recognizable voice. The situation would change if I could change the speed of sound in my system. And helium, which has a very different molecular weight from air, has a way higher speed than the speed of sound in air. It's about 2.7 times higher, 2.7 times 340 meters per second. So if I fill my system with helium, apart from the fact that there's no oxygen in helium, so I wouldn't survive very long, that's a detail. If I fill my system with helium, then, of course, my vocal cords and my sound cavity here, they don't know that, so they do the same thing that they normally do when they speak to you. However, since the speed of sound is much higher here in my sound cavity, the frequency that it will produce is way higher. And I sound very differently. The problem, however, is, as I mentioned, there is no oxygen in helium. And yet, if I only take a little bit of helium, it doesn't work very well. Then you don't hear much difference. So I have to really take a lot of helium. And I will try that. But for that, I pay a small price. And the small price is that you can faint. I'll try just to stay away from the fainting level. So here is helium. And I have to let my air out first, and then get helium in, and maybe let the helium out again, and let the helium in again. And during that time, I can't speak. But then, when I think I'm full enough with helium, I will say a few words to you. So let's get the pressure up to the level that I like.
I told you it would sound very differently.
Well, I hope you enjoyed this, and I'll see you Wednesday. Thank you.